Okay, yeah, thanks. Please go ahead, Francis.
Okay, so yeah, so I think this should be the last talk. Uh, so I'll just start by kind of recapping where we left off. So remember the setting was generalized scalar structures of symplectic type, which are possibly degenerate. And if you remember, this was the following structure. So it was, comes down to this collection of 4 tensors where we get 2 holomorphic Poisson structures. So something like this. F is a closed 2 form. So it's a real 2 form. So closed, real 2 form. Such that satisfies the following 2 equations. That the difference between the 2 complex structures is measured by the Poisson structure and the 2 form. And this 2 form satisfies kind of a joint 1-1 condition. So this was the structure. And I mentioned this at the very end. I think I mentioned this at the very end, that if you look at Marco's paper, which was brains on Poisson varieties, he has the system of equations, and one way of thinking about it, which maybe it will be useful, it's useful for some people, if you know what this means, it says that F gives a B field equivalence between the Poisson structures sigma plus and sigma minus. So this is only for the people who know what this means. Otherwise, it doesn't matter. Okay, and then the main theorem is a reformulation of generalized scalar geometry of symplectic type in terms of what I talked about last time, which are these holomorphic symplectic Morita equivalences. So the theorem says that we have a bijection or a correspondence between GK structures of symplectic type and holomorphic symplectic Morita equivalences with brain bisection. Actually, I'm going to put this on the next page and draw a picture of what's going on, just to remind you of the definition of a Morita equivalence. So the picture that I like to have in mind is the following. We have this big space here, Z omega, which is a holomorphic symplectic manifold. Here's a picture of it. And the property that it has, well, first of all, it has these two maps, pi plus and pi minus. And they map to the base manifold M, but equipped with the Poisson structures. One of them is sigma plus, and the other one is sigma minus, like this. So if you recall, so pi plus and minus are holomorphic, and they're also Poisson maps. So here on Z, we have this symplectic form, but we can invert it to get a Poisson structure. And we can push it forward with pi plus or with pi minus. And that will be equal to either plus or minus the Poisson structure. So if you use pi plus, it pushes forward the Poisson structure on Z to sigma plus. If you apply pi minus, it pushes forward the Poisson structure on Z to minus sigma minus. So that was one of the properties of one of these spaces. And we can draw the fibers of the maps. And these have the property that, that they're orthogonal when you pair them with the symplectic form. So the kernel of d pi plus and the kernel of d pi minus are orthogonal with respect to this pairing. Okay, so that's the Morita equivalence. And the claim, which is kind of substantiated by this theorem, is that this Morita equivalence, it represents the holomorphic geometry underlying a GK structure, at least of symplectic type.
I'm sorry, Francis.
Yeah.
Can you just remind me? So sigma plus minus are the I plus minus imaginary parts of the commutator of like the.
So Q
no.
is, so let me just do it on this page here. So Q.
Oh, sorry. Never mind. You wrote it above. I see.
Yeah. It was something, I forget exactly the formula. I think maybe minus 1/2. Something like this.
Oh, okay. Yeah.
So for this, in my definition of generalized scalar structure, I'm kind of taking Q as a kind of a primitive structure.
Yeah.
Which is the common imaginary part of two holomorphic Poisson structures, sigma plus and sigma minus. But when you formulate a generalized scalar structure in terms of Riemannian metric, which has two complex structures with its Hermitian, then Q can be written in terms of the commutator.
And the theorem is like a strict generalization of the Kähler case, like where I plus equals I minus, and then Z omega is just the Donaldson one you described.
Mhm.
And it's
Yeah.
even sort of like the whole construction is like smooth in a family, right? So there's these kind of like Hitchin type deformations of Kähler into generalized Kähler symplectic type on Fano surfaces. And then the whole process is like smooth. This association of Z omegas.
Uh, well, sort of. So I'll talk about that a little bit in some examples. It's true that if so, I'll explain how the flow construction relates. It kind of fits into this picture, and that was the construction. Remember that we could take a Kähler structure and deform it. That sort of works in this case. There's one kind of key difference, which is that the topology of Z, it's not necessarily the cotangent bundle. So
Nice.
you can kind of have a family, but which will be kind of a smooth family that will kind of start at Z and degenerate to the cotangent bundle or like an affine deformation of it. But the topology will change.
Okay.
Um, yeah. Okay, so yeah, so the remaining structure is this L. And L is a brane bisection. So the properties of L are that pi plus or minus restricted to L gives you a diffeomorphism. And if we take omega and we restrict it to L, it's real. Well, L is Lagrangian for the imaginary part of omega. And L, it kind of it represents the metric, or it represents the kind of the C infinity structure, the real structure. And the way that the correspondence goes, so let me just say one direction of the correspondence. So given this structure here, we want to produce a generalized scalar structure on, we can actually just put it on L. So the GK structure is going to be, it'll be like pi plus inverse of I plus, sorry, it'll be, we want to take pi plus restricted to L and pull back I plus, pi minus restricted to L, pull back I minus. Q will be the pullback with either plus or minus of the imaginary part of sigma plus or minus. And finally, F will be the restriction or the pullback of omega to L. So the brane L is kind of playing two roles, right? One of the things is that we want I plus and I minus to be on the same smooth manifold, but right now we have two separate manifolds. So using L, we kind of use L to identify the underlying smooth manifolds of L, this one and this one. So they kind of all get identified. And so we can just transport I plus and I minus to this thing. Same thing with the Poisson structure. And then for the two form, it's just, we take this holomorphic symplectic form and we restrict it to L.
Sorry, I don't understand one thing. So this, a priori, this Q, you don't have it I see that you have I plus and I minus from the Ricci equivalence. And by the way, if you have F, this ultimately will determine Q. But where is Q? Where Q leaves now?
So you have, yeah, so that's the interesting thing. So you have sigma down here, and you can pull it back to L. So you could pull back sigma minus to L, and you could pull back sigma plus to L. And these will be different Poisson structures. But because L is a Lagrangian for the imaginary part of omega, that will actually imply that when you pull them back, sigma minus and sigma plus will have the same imaginary part when restricted to L. Yeah. So that's what I tried to indicate this, that you can either pull back the imaginary part of sigma plus or sigma minus, and it gives the same thing. Okay, are there any other questions about this? So let me just make a brief remark. So back when I explained the Donaldson formulation of Kaler geometry, there were 3 constructions. One was kind of the affine deformation of the symplectic groupoid. And that's the one that's kind of easiest for this theorem. That's kind of the easiest one to generalize. That's the one that I explained last week. So that's the one that we give in the paper. There's also the check description, which is the kind of the first one that I presented. So this also works, but it's not as nice. But if you're interested, I explained how to do this in my thesis. And then the third description, that was the one where I used, if you're in the case where your Kaler structure was pre-quantizable, then using the line bundle, you can also construct the space that way. This thing also generalizes, at least in certain situations where you have to use Poisson line bundles. This hasn't been written down, but Marco and I are writing a paper where it is useful for us. Yeah, so I just wanted to mention this because I had presented those 3 constructions in the Kaler case. So just in case you're curious whether those things generalize, the answer is yes. Okay, so let me just give a couple of examples of this. So the simplest example, remember, we have this kind of degenerate generalized Kaler structure associated to a holomorphic symplectic groupoid, holomorphic Poisson structure. Remember, it was just you take I, you take the imaginary part of sigma as Q, and then for F, you just take 0. So that was kind of like a really degenerate example, but that's useful in constructions. In this case, the Morita equivalence is the symplectic groupoid. Of the Poisson structure, and L is the submanifold of identity arrows. Okay, so that's kind of a trivial example. Here's another kind of trivial example, which is well, it's not trivial, but it's the one that we already saw, which is the Kaler case, where we have, so it's kind of degenerate in a different sense, that the two form is symplectic, but the Poisson structure is 0. And remember, this is what I presented, that it's just the cotangent bundle, but you take the canonical symplectic form and you add the pullback of the Kaler form. And then for L, you take the 0 section. Okay, so here's maybe a slightly more interesting example, which is a Hyperkaler example. So if you have a Hyperkaler manifold, then the generalized scalar structure that you can get, you kind of have to break the symmetry to do this, but one generalized scalar that you can get out of this is as follows. And in this case, the holomorphic Poisson structures they come from holomorphic symplectic structures. You have one for I plus, and you have one for I minus. Then the Morita equivalence, you take it to be the product of these two holomorphic symplectic structures. And for L, you take the diagonal copy of M. Okay. So those are just some kind of simple examples. In the kind of, they're kind of the extreme examples where either where the symplectic form or the two form F is degenerate, or where the Poisson structure is degenerate, or where everything is kind of maximally non-degenerate. Okay. So now I'll talk about the kind of the main subject, which is the generalized scalar potential. And actually, I think there's kind of...
Can you recall again in this picture, how do you detect the positivity of the metric?
So you have to define, so the metric, so given kind of this type of structure, I plus I minus Q and F, G, no, I forget the formula. It was something, yeah, it was something like this: 1/2 F times I plus I minus. So this is a symmetric tensor.
Maybe for those who do symplectic geometry, I think F tames I plus and I minus. So the 1/1 part of F gives a Hermitian form with respect to either.
Yeah, that's right. Yeah, you could take the 1/1 part of F either with respect to I plus or with respect to I minus. Yeah, thanks. Okay, so the generalized scalar potential. So there's kind of there's actually two ways of generalizing the Kaler potential to this setup. So I'll just kind of explain that there's kind of version 1 and version 2 And whichever one you would prefer, it kind of depends on which situation you're in, what you want to do. So here's the kind of the idea. So remember, the submanifold L, this is what defines the metric in a sense. And so we want to describe this. So we want to describe the metric in terms of a single function by taking derivatives. So we want to describe L using a single real function. And the way to do it now is kind of clear because L viewed inside of Z with the imaginary symplectic form is Lagrangian. So we can describe it using a generating function. So I'll just describe the kind of the details of this. So for this, we should choose a holomorphic Darboux chart. So that's some extra structure that we should choose. Here's kind of a picture. Something like this. We have inside of here L. More precisely, what we're doing is we're choosing an embedding of the holomorphic cotangent bundle of some kind of holomorphic Lagrangian. We're choosing an embedding into Z, omega. Once we've made this choice, as long as our choice is kind of generic enough, then L, it just becomes the graph of a 1-0 form. And because L is Lagrangian with respect to the imaginary part of omega naught, that means that omega naught restricted to L, which is d eta, this is real. So in other words, the imaginary part of this one form eta is closed. So locally, at least, the imaginary part of eta is equal to the derivative of a function k. And k here, it's a real function, and it only depends on half the coordinates, right? It only depends on kind of the base of the Darboux chart. So k is something that depends on q and q bar. Okay, and so then since eta is a 1-0 form, we can write it as taking the kind of the del operator applied to k. And therefore, f, which is part of the metric, I mean, it's kind of equivalent to the metric. It's given by d eta, which is del bar of k. So this k here is the generalized Kähler potential. Okay, are there any questions about this?
So I understand this is only local, but let's say first Betty number is 0 and we want f to be in a given Durham class. Is there any chance that this will be a global statement?
That
or the variation of f, let's say in families when you want to formally move the construction, can you state that it's a dd bar of something global?
So for this way of defining the generalized Kähler potential, it really depends on being able to choose this Darboux chart. And maybe kind of one difficulty is that like Z might be kind of, Z might not have a global Darboux chart or something like that. The second version that I will present, it will be much more along the lines of what you're asking about. So let me just postpone answering your question until later. But there are some cases. So I'll just give some examples. So there's some cases where we can choose a global Darboux chart, or at least kind of a big enough Darboux chart in the groupoid or in the Morita equivalence, where we kind of get something global. And it's kind of an application. You can construct new. You can use this to construct examples. So so here's the way that the structure of the example will be the following. We'll start with a holomorphic Poisson structure, and then we'll try to construct a generalized scalar structure which has that underlying Poisson structure. So let's take our manifold to be C2 and the Poisson structure to be T times X del X wedge Y del Y. So in this case, the symplectic groupoid it has a global Darboux chart. So I'm gonna write the symplectic groupoid with the global Darboux chart. So as a space, it just looks like C2 times C2 with coordinates X, Y, A, B. And remember, we have these two maps going to C2. One of them I'll call it S. It takes X, Y, A, B to e to the minus T, B, Y times X, Y, and something similar on the left. And in terms of these coordinates, the symplectic form is dA wedge dx plus dB wedge dy. So this Z, it's actually a symplectic groupoid. So it's not just a Morita equivalence, it has more structure. And so remember, I kind of mentioned this here in this first example, you kind of get a canonical, really degenerate generalized scalar structure where the form is just 0 by taking L to be the kind of the identity arrow. So in this case, it would be X, Y, 0, 0. So this is kind of a boring example. But if we want to get an interesting GK structure, we can choose another brane. And in order to do this, we just need to choose a real function of X and Y. So we need to choose a real function K of X and Y. Does the kind of the logic of the example make sense? We have the underlying holomorphic geometry at this point. We just need to choose the metric, which now just comes down to a single function. So here's one choice, which is kind of looks a little bit perverse. So here, this Li is the dilogarithm function. But if we do this in this case, then we get the following two form. Which is symplectic. So when we do this, we get a metric G. On R4. It will be a generalized Kähler metric. I won't write down the expression, it's a little bit complicated. It's not that bad, but and well, this won't actually, I mean, just because we've chosen all of the structure, it's not guaranteed that that G will be positive definite. So that's something that you have to check. And in this case, for for T between 0 and 1, we get a metric. And for T strictly less than 1, it's complete. And at T equal to 0, then we get a Kähler structure. So I think this is relevant to your question, Jeff. When we take T equals to 0 here, if you look at these maps, this part here goes away when T is equal to 0. So this space actually becomes the cotangent bundle. And so this just becomes a Kähler potential. But when we turn on the Poisson structure, it kind of deforms these two maps. It kind of deforms them out, and that kind of deforms all of the structure in a consistent way. And it still remains generalized Kähler for small enough values of T.
And can you say what the associated Q is as a function of T? Oh, never mind. I guess it's up there in sigma. I guess once.
Yeah, Q is the imaginary part of this.
Yeah. And also, I guess in general, the sort of positivity condition you need for K is maybe nonlinear. Is that right? Or
yeah, I think it's a little bit complicated. So yeah, it's a little bit complicated to analyze. So I did it for, I analyzed it in my thesis when you have the case of toric Poisson structures like this here. So I'll give another example. It's still the same kind of structure here. It's the same holomorphic structure, but I'll choose a different potential.
Can you just comment on why it's important to take the D logarithm? What is the role played by the D logarithm?
It's just an example that gives you a complete metric. If you choose the one that you would expect, like this one, then it will only be defined positive definite on some disk, like on some finite region, and it won't be complete. So this, I guess this dilogarithm, it kind of has the right growth rate in a sense.
Okay.
So here's another choice. So this is the Kähler potential for the Fubini-Studi metric on CP2. So in this case, we get a generalized Kähler metric on C2 that extends to toric generalized Kähler on CP2. And it works for the norm of T less than a fixed constant that you can work out. And at T is equal to 0, you get the Fubini-Studi. So this kind of technique here, and you can kind of do it like with a check method. So this gives a general construction for toric generalized scalar structures deforming Kaler structures. So it works in general. In my thesis, I kind of analyzed the positivity of the metric in the case of surfaces. An analog of that, I mean, when you go up in dimension, it just becomes more difficult to analyze the positivity. And maybe a remark again. So there was work by Boulanger.
Sorry, what is said in this second example?
It's the same one here. Where is it? Yeah, it's the same space. If you want to kind of complete it to CP2, then it will kind of live on the cotangent bundle or a deformation of the cotangent bundle. So it will be like in the Donaldson case, but instead of having the projection, those will be deformed to different maps. So examples like these, they're kind of this version of the generalized scalar potential works really well. So I just wanted to mention that Boulanger gave a construction of toric GK based on the symplectic potential so you might ask how the two are related, but for his examples, he needed to require that T is imaginary. So this parameter T here, which is the kind of the parameter that I'm deforming. So in Boulanger's work, he needed that T was imaginary. And in this picture, T should be real. So in fact, you can still do this even when T is not real, in the sense that you can still run, you can still do the deformation from Kaler to generalized scalar, but the K has to get deformed in a complicated way. So yeah, it's still, yeah, it looks like the two, the symplectic potential and the Kaler potential are kind of adapted for different situations.
So is it right that you're changing the real part of the Poisson structure and then Boulanger is not, or vice versa? Or is that not the point?
In both cases, you're scaling the Poisson structure, just rescaling it. But I guess for him, the imaginary part is different. Like the imaginary part and the real part are swapped in the two cases.
Okay.
Like his imaginary part is my real part. Right, because you're just taking the Poisson structure and multiplying it by I.
Oh, okay. But I mean, but they are geometrically distinct, or you're just saying it's like a different notation or something?
The Poisson structures are not isomorphic.
Oh, okay, yeah.
And not, Yeah, they're not isomorphic.
Well, I guess I don't mean as T changes. I guess I mean like your family versus his family. Are the families geometrically distinct?
Yeah, they're not isomorphic.
Okay.
I think they're not isomorphic.
Can you say again where does it play a role that T is real in your picture? I mean the holomorphic Poisson structure and the symplectic groupoid, I guess it doesn't matter. It's just for defining the Keller potential and to obtaining a complete metric. Is that the thing?
So the place where it's kind of relevant is, so once you choose K, it defines this submanifold inside of here.
Yeah.
And you want the restriction of T and S to L to be a diffeomorphism, first of all. So that's one thing that you have to, that might break. But when T is real, it's going to be true for all time. So that's the first thing. And the second thing is analyzing when the metric is positive definite.
But the the construction exists, right, for any value of T. It's just a question of whether you get a bisection or whether you get a positivity. But I mean, certainly for any value of T, right, that defines this bisection, you're at least going to have something that you could call a degenerate GK structure, right?
That's right. Yeah. Yeah. And the comment I wanted to make here is that you can run the deformation from Kaler to generalized Kaler, but in that case, okay, you could take L to just be the graph, but the kind of the natural choice is to deform L in a specific way as well. And then when you deform L, that means that you'd have to deform the potential in a complicated way.
Yeah, but there's a bunch of different things happening at the same time. Some of them are your choices, right? And some of them are the point is that you have in the T line on the complex plane, for every value of T, you have a holomorphic symplectic manifold with these maps. You have this holomorphic setup that varies in the T plane, right? And for any one of these, if you choose a bisection, which a smooth bisection, that's like a very arbitrary choice, then you're going to get a GK structure. There's nothing special about the real line or the imaginary line or whatever. I mean, it's a particular thing about how you want to build that function, right? I mean,
yeah, that's true.
I just want to make sure that that there's no impression that somehow, from the holomorphic point of view, there's something special about values of T.
That's true.
I mean, if you're, in other words, if you're trying to move off of the imaginary axis, it's going to work for a while because these are open conditions, right? So any example that you find, you can deform it however you want, and it'll be perfectly good for all values of T in a neighborhood, no problem. But if you go too far, then there will be some singularities that may happen because you chose the wrong function, basically.
Yeah, that's true.
Yeah.
Yeah.
And the difference between your construction and Boulanger's construction is that the function is different. Right? I mean, the bisection is different. I mean, he's making a choice of bisection along the imaginary axis for these values of T, which doesn't work for elsewhere if you go too far away. And you're making a choice which is valid and perfectly good for a neighborhood of the real axis, right?
Yeah.
Which presumably doesn't work if you go too far away. But it's just a choice. That aspect of it is a choice.
Nice. Thank you. Yeah, that's that.
Okay, so wait, what number was I at? 3. Okay. So yeah, so now I want to describe how this relates to the flow construction, and then I'll describe the kind of the second way of generalizing the Kähler potential. So there are natural ways that we could deform the setup. So one thing that we could do is we could deform the holomorphic substructure. Okay, so that would be like deforming the space Z and the holomorphic symplectic form. The second thing that we could do is we can deform the brane L. And a kind of a useful way to deform that, if we want to ensure that it remains a brane bisection, is to deform it using a Hamiltonian flow. So we can deform the brane L using Hamiltonian flows. And these types of deformations, they give rise to the flow construction. So let's just recall the kind of the basic, the simplest form of the flow construction, which was the following. So we have M I plus minus QF corresponding to Z omega L, and we have F, a real function. And remember how the flow construction works. We took the Hamiltonian vector field of F and this 2-form omega, which was dd bar of the function. We flow the vector field. Then we can deform our generalized Kähler structure. So we deform I plus by just flowing it using the vector field. I minus stays fixed, Q stays fixed, and F gets deformed as well, like this. You basically take dd bar of the function and average it over the flow.
Sorry, what happens with the initial F? Probably you have F0 plus that guy?
Yeah, that's right. So F0 plus this.
Oh, okay.
Yeah, and this deforms the GK structure. And the result, or the theorem, we can describe this in terms of deforming this Morita equivalent setup. So this family corresponds to deforming L via the Hamiltonian flow of a vector field on the space Z itself, it's the Hamiltonian flow with respect to the imaginary part of the pullback of df. So,
sorry, Francis.
Yeah.
The dd bar in every place is like the I minus dd bar. Is this right?
So here it would be with plus. You can imagine it's like we have I minus, I plus, and then we're kind of deforming to I plus t. Does that make sense?
I mean, yeah, it makes sense. I thought it was the other way back. Okay, yeah.
It depends on which thing you want to deform. So like here, we're deforming I plus. Oops. And I minus stays fixed. If we wanted to deform I minus and keep I plus fixed, then here we would put in, it would be with respect to the minus.
Yeah, okay.
There's kind of more general theorems along these lines for the more general flow constructions. But let's just keep it at this one.
Can I perhaps ask my usual question? So in this construction, the flow construction, so you fix essentially the Poisson structure. So Q is fixed. And clearly the cohomology class of F stays fixed by the formula you showed us. Can you reverse this? Can you say that under, let's say dd bar lem or something, some condition, can you say that any generalized scalar structure of symplectic type with symplectic formula given the RAM class is of that form, or?
Yeah. So that will be one of the results. But essentially, it's, if you deform the brain, then locally it will be deformed using a closed one form. Whether or not it's exact, I'm not sure. Probably, maybe it follows from.
Yeah, it's some sort of dd bar lemma you would need at this point, perhaps.
Yeah, but at least it flows by a function, or sorry, by a closed form. Yeah. So let me just give two examples of this. So one of them is if we start with a holomorphic Poisson structure, my sigma. So remember, this gives us this degenerate GK. And the Morita equivalence, which is just the symplectic groupoid with the identity arrows. And then let f be a function, a real function. And then we take the Hamiltonian vector field on the groupoid and take its flow phi t. Then we can deform the brain by just applying this flow to the identity arrows. And this gives us a GK structure where the two form is exactly this deformation. So I guess that's a special case of the one above. Another example is the one that I spoke about last time, It's this deformation of a hyperkaler structure. So remember, we got, in this case, omega plus, which is like this. Omega minus was, and then Z omega L, it was M with omega plus times M with minus omega minus, and L was the identity, sorry, the diagonally embedded copy of M. And then given F, so we can do this construction here. So if we take pi plus pullback of df, so pi plus is just the projection to the first factor. So that just gives us this form, df only on the first factor. And then if we flow with the imaginary part of omega, which is omega k, minus omega k, sorry, then the Hamiltonian vector field will be just of the following form like this, where VF is the Hamiltonian vector field with respect to this omega k. And so what that means is that once we flow to get this deformation of the hyperkaler into a generalized scalar, then L of t, it will no longer be the kind of the diagonal copy of M. It's going to get deformed by the flow of this vector field. It's going to be the elements that look like this. So in other words, it's just going to be the graph of the flow. Okay, does this make sense? Okay, so I just wanted to end with the last thing, which is the kind of the second way to generalize the Kähler potential. So this is, so let me draw the picture. So this is a generalization that is kind of more adapted to the Poisson geometry. And so it's more useful for some perspectives. So here's the kind of the picture that we have again. Here's L. Remember these maps, they have these fibers. Okay, so to describe the potential, the kind of the second version, it requires a couple of steps and a couple of choices. So before, like the main choice was choosing a Darboux chart. For this one, the choice is step one, is to choose a local holomorphic Lagrangian bisection. So I'm going to draw this here. And this is a holomorphic Lagrangian. And it's a section of both of these maps. So it identifies an open here, an open here. It will So what this will do, it will induce isomorphisms between the Poisson structures locally, but it will also induce an isomorphism between this space Z omega, the Morita equivalence, and the symplectic groupoid of one of the Poisson structures. So this is the symplectic groupoid of the minus Poisson structure, say, at least locally. So this is like a Darboux chart. If we were working on the cotangent bundle, it would be a Darboux chart. But in this case, the kind of the chart is like a groupoid chart. Okay, then for the second step, we choose a family of brane bisections, LT interpolating between L and this holomorphic one. So we kind of choose a family that kind of goes between them. And the basic fact about these families is that they're generated by functions. So this family is induced via the flow construction applied to I minus, sigma minus, and a real time-dependent function, ft. So essentially what this is saying is that this example here, where we start with this kind of degenerate GK structure of a Poisson structure and deform it into an actual GK structure using a function, that's locally, that's true. That's how all generalized scalar structures look. So you kind of get a theorem, which is that any GK structure of symplectic type is locally of the form I plus. So here I plus is going to be the flow of a function applied to I minus, and F is this kind of integral that we have in the flow construction. So here, this is the flow of Q df. Okay, so this gives kind of an alternative generalization of the Kähler potential. Again, if you do this in the Kähler setting, it will just give you back Kähler potential. Yeah. Any questions about this?
Sorry, you, but even this, I mean, it seems like conceivable that you could describe globally another Lagrangian bisection as like a graph over the given one somehow.
Yeah, that's right. So I think like
is that possible ever?
I think there could be some. So it's kind of like the question of if you have two diffeomorphisms and they're close by, can you find a vector field that kind of relates them?
Yeah.
So it's a question about, it is kind of a question about if the exponential map on an infinite dimensional Lie algebra is a local diffeomorphism. So.
But the thing is that there is an abstraction, right? You cannot expect to find this green holomorphic Lagrangian. I mean, that Z omega, it has a certain cohomology class embedded in it. It's genuinely a deformation of, just in the same way that the twisted cotangent bundle is not isomorphic to the cotangent bundle. There's an abstraction, which is that if you look at the zero section, the twisted cotangent bundle has a class that evaluates on that section to be non-zero in cohomology. So when you take the cotangent bundle and you turn on that symplectic form, that is moving it in the complex moduli. And it is no longer going to have a global holomorphic Lagrangian bisection. Like it used to. It used to have the zero section. But as soon as you move away from the cotangent bundle, it does not have a Lagrangian bisection anymore in the holomorphic sense. That's why it can only have this half, it's like imaginary Lagrangian bisection. So the funny thing is that it's very important in this part 4 here that the green thing is local, because you can't find a green holomorphic Lagrangian transverse to these.
I guess also
it's kind of like.
Sorry, go ahead.
I understand that, but just infinitesimally, if you start with something and you move a little bit, so then perhaps you can always do this, but with closed one form or something.
That's true. If any deformation of the brain will be given by a closed one form.
You have this aptly obstruction that you're talking about. Perhaps if B1 is not trivial, and you will have something which is not globally the of a function, but maybe in some cases this would be possible to do. In the Tori case, for instance, I believe B1 is 0, and what these results show, Boulanger and Wong, is that actually somehow it's true globally. This deformation with a Hamiltonian function.
For that one, you also have to deform the cotangent bundle, though, I think.
Yeah. Mm-hmm.
So I think like one way to think about it is that if you wanted to construct an interesting GK structure on a compact manifold, let's say that you started with a compact Kaler manifold with a holomorphic Poisson structure. Then initially it's Kaler, so you should think of that as being like the Poisson structure is off. There's no Poisson structure. But then when you try to turn on the Poisson structure, and that produces you a one parameter family of Poisson manifolds. Okay, the initial one, when the Poisson structure is off, the holomorphic thing that lives above that compact Kaler manifold, that holomorphic Z space, that's the twisted cotangent bundle. So at t equals 0, you have the twisted holomorphic cotangent bundle. And then the problem is that thing needs to be deformed. So you can, if you want to turn on the Poisson structure, you need to deform that into one of these Morita equivalence gadgets. And then what you need to do is take your Lagrangian section that you had originally that defined your Kaler manifold, and you need to take that Lagrangian bisection and drag it horizontally for different values of t. So it would be like, the type of problem that it would be like, number one, you would have to do a Hitchin deformation. Well, you could think of it this way, that you turn on the Poisson structure and then you want to deform the brain along with it. So it would be a deformation of a pair. That's the only way that I would know how to do it globally, without making these local choices.
So I wanted to finish maybe, yeah, I mean, basically this is all I have. But there was this, maybe a couple of questions that are kind of open questions. Here's kind of a technical one. I don't know how interesting it is, but here it kind of shows that you can, that any generalized Kähler structure is locally a flow construction away from a holomorphic Poisson structure. So it's something like this. Where at f of 0, we get 0. But remember, there was this kind of, this other way of viewing the deformations, which is that we can put a factor of t in front of q, and then put a 1 over t in front of ft. And so now at t is equal to 0, well, this part vanishes, but this thing, when t is equal to 0, just gives you this. So my question here is, can we do this so that all the 1 over tft are positive? So that we actually get a deformation of generalized Kähler structures that ends up at a Kähler structure. So I don't know if that's true, but.
All right, maybe I just don't understand. I mean, how is this? Oh, I see. You want to let the Poisson tensors go to 0?
Yeah, so like the way that I described it, it's a family like this. So it's like the Poisson structure stays the same, but at time equals to 0, the symplectic form gets killed. So you just have a holomorphic Poisson structure, which you're deforming away from.
Isn't this this feels like it's sort of just you're sort of like reversing the Hitchin construction, aren't you? I mean, there you're turning on the Poisson tensor. Isn't it sort of?
Yeah, exactly. So
already
this is
implicit in what he does?
Or? Well, he gives a method of deforming a generalized Kähler structure or a Kähler structure. But this is the question of, is any generalized Kähler structure locally obtained by deforming a Kähler structure?
Oh.
So here, this is a result of this form, but it says that every generalized Kähler structure is obtained locally as a flow construction away from a holomorphic Poisson structure.
Oh, okay.
So the kind of the local data that describes a generalized Kähler structure, it consists of a holomorphic Poisson structure and a single time-dependent real function.
I see.
But my question is, can you do the deformation like this so that these forms remain positive definite, so that the metrics remain positive definite, so that it's actually a deformation away from a Kähler structure? Yeah.
Locally. I mean, you're just asking locally, right?
Yeah, that's right. Yeah. I mean, this is just something that I was always curious about, which I never really looked into. Here's another question. Well, one question is just, how does this work? Or how does this generalize to non-symplectic type GK? That's kind of a natural question. I believe Marcos has a student working on this, which should be an interesting project.
It's Yusang. Yusang is working on it.
Right, yeah. So
Yusang Jiang.
Another question which I was always kind of wondering about is how the generalized scalar Ricci flow fits into this, which I guess this is something relevant for this seminar.
I'll be talking about that next.
So already based on the current literature, there's kind of, you can already say a little bit of what's going on, because so the generalized scalar Ricci flow, it gives a deformation of the following form. So it's a deformation where this part stays fixed, but so only one of the holomorphic Poisson structures is deforming. So, but you have both the holomorphic substructure deforming and L of T deforming. So there's kind of two questions. One is, what is the deformation of just this thing, of the holomorphic symplectic structure? And this is actually contained in a paper of Gibson and Streets, which relies on the following fact, which is that a Poisson module for, say, I plus, sigma plus, this is like a Poisson line bundle, it gives rise to a deformation of Z omega T. That's one fact. And another fact is that the canonical bundle of a holomorphic Poisson structure has a canonical Poisson module structure. So I think this is contained in a paper, although I don't understand the details. But I think it's implied from these observations, these two facts, along with a result in this recent paper, that the deformation Z omega T in GKR flow is the one generated by the canonical bundle. And so then the remaining part of the deformation, the remaining flow, is a deformation of LT, and this is controlled by either a function, time-dependent function, or maybe a one form, a closed one form. And so I guess the question is, what is the function? And there's already a case where this is known. So when the Hitchin Poisson structures sigma plus minus are invertible, then Z omega T does not deform. So in this case, the Ricci flow is completely described by a function or a one form. And I think this is in a paper, which is the so-called Ricci potential. Because in their paper at Postlov and Streets, they write the generalized Caylor-Ricci flow exactly as well, exactly like this type of, exactly like a flow construction. So if you kind of translate that into the picture of the Morita equivalence, it will just be flowing the brane by the Hamiltonian flow of that function. So at least in that case, I mean, this question is already known. So I guess my question is, what is the function in general?
But Francis, you don't remember what I was working on with Joey for 2 years? Like 4 years ago? I mean, I'm kind of surprised. So the point is that the canonical line bundle, right? So if you have this thing that is a bimodule from x minus to x plus, right? Each of x plus and x minus, they're Poisson manifolds. And they have Poisson modules because they have canonical bundles. Mm-hmm. And anytime you have a canonical bundle, it gives you a Poisson module, like you're saying here, right? And that Poisson module defines a Hitchin deformation. But it's not just a holomorphic object, it has a metric on it. It has a Hermitian metric. So the Hermitian metric on the canonical line bundle is what dictates the deformation of the Z space. And you could do that on the left and you could do it on the right because there's two canonical bundles. And in fact, you could do it for any Poisson module. There would be a corresponding Ricci type flow. Yeah. It's just called the Ricci flow because it's the canonical bundle. So you get the Ricci tensor as the curvature of the Chern connection. That was the thing that he was writing up when he left math.
Oh, so actually the answer to the function?
Like I said, it's not just a holomorphic object. It's a Hermitian line bundle. It has a metric because it's a generalized Caylor manifold, and that metric induces a Hermitian metric on the line bundle.
Right.
Well, I mean, there's still, I guess, maybe the question of the actual function ft. And I mean, basically, you can say, in general, it's essentially always the Ricci potential, where the meaning of Ricci potential. I mean, I'll spend some time talking about this soon, but it's always, it's what you call the Calabi-Yau. It's just the Calabi-Yau quantity that you write down in your thesis, Marco. This is how I guessed all of these things, that somehow that had to be the right function. And basically the general formula that holds locally is that if you have the two generalized complex structures defined by some pure spinors, and you take the log of the ratio of the two spinor norms, right? This,
but the thing is that
is in a sense,
I think you're absolutely right. But the thing is that you don't have a pure spinor in this case. You only have one of them.
No, I understand.
Right.
Well, right. So what I said is only true locally.
Right. So the replacement for the function in general would be the Hermitian structure on the line bundle. You could think of that as a kind of like a function.
Well, yeah. Okay, yeah.
Or another way of putting it is that if you go to the total space of the canonical line bundle, that one is Calabi-Yau. It does have a pure spinor, and then the formula is exactly the one you said.
Yeah.
And so you could work, for example, on the total space of the canonical line bundle instead, and you would get a global result. You would get a single function, which would do the job for the compact generalized scalar, even if there was no Calabi-Yau.
So does it agree with this? So it recovers the scalar potential, or sorry, this?
Yes, of course, yeah.
Is this written somewhere, Marco?
Well, no.
Let me be the first to invite you to please write it up. I would very much like to see it.
Well, I mean, it's unfortunate when a postdoc goes all of a sudden for no good reason to the private sector after having written half of the nice paper. So, and then I guess it's supposed to be my job.
Can you just repeat one more time? You said you somehow lift the structure to the canonical bundle itself?
Well, one way of working, like anytime that you have a GC structure, right? Let's say you have a GC structure on a compact manifold, and maybe you're annoyed at the fact that you don't have a global pure spinner.
Yeah.
That it's not Calabi-Yau, right? But that GC structure, it has a canonical line bundle, always.
Yeah. It's
a complex line bundle which has a certain kind of connection on it.
Yeah.
And if you work on the total space of that bundle, it's always generalized Calabi-Yau. Okay. So as long as you work C star equivariantly on that bundle, it's the same thing as working on the base. It's just that now you have a pure spinner.
I see. Okay.
So you could do the same thing. You could I mean, a lot of the things that Goto does, for example, they become a lot clearer when you look at it that way, because he's always insisting on the choice of like sometimes when he chooses the pure spinner, it's important. Sometimes it's not. It kind of depends on what he's doing with it.
I see. So yeah, I mean, maybe it's a good lead-in for my talks. Yeah, I'll talk quite a bit about this relation. I mean, the long story short is that basically in every case that I understand well, the generalized Caylor Ricci flow is doing exactly this flow construction. I mean, it's exactly of that form. Yeah. And maybe I just ask again, Francis, I already asked the same question like 3 times, I guess. But so, I mean, at least locally, you do derive truly this one scalar potential that describes everything. But then sort of a bit more globally, you can think of it as driving a family of, you can think of one function as driving a family of generalized Caylor. But of course, yeah, I mean, the Holy Grail, and even when I talk about deforming, I mean, for me, a lot of the time, I'm even happy with like the Hyperkaler case where no cohomology is moving. The Poisson tensors are not changing. Everything's fixed. I mean, the Holy Grail would be in some sense to describe the structure globally in terms of background data and one function. But it just, maybe this is just something I have to give up on. It doesn't seem possible. I don't know. But I don't know if you have thoughts.
Can you say that again? What is the Holy Grail? I don't know about that.
Well, so I mean, yeah, I would like to, so for instance, let me just fix the simplest case, like Hyperkaler. And then your flow construction sort of preserves everything. The sigma will be fixed. One of the complex structures is fixed. Of course, the other one will change, right?
But don't worry about the flow construction so much. Like, what is the
well? You want to have the generalized Caylor Ricci flow is a flow construction. So I mean, you want to describe
the I'd like to just flow in terms of a single scalar function,
which sort of we have done, because as we said, it sort of is one of these flow constructions. So infinitesimally, it's driven by one function, but all the analysis of Caylor Ricci flow somehow relies on the global description of your time-dependent Caylor metric in terms of background data and one function. And this plays an indescribably large role in the analysis. And as far as I can tell, in most cases, this is just missing.
In most cases? What do you mean in most cases? Like non-Hyperkaler?
Well, so we have this work coming with Vesti and Yuri, where in the toric setting, you can do it. You can get this global description, very much like a sort of standard Caylor potential. Yeah, I mean, I'd like to be able to sort of coherently describe the time t data along the flow in terms of one function, as opposed to a family of functions and a diffeomorphism action, right? But maybe it's, I don't know. I can't quite get a sense if one should expect that is even possible or not.
But for example, if you have a GK structure of symplectic type, and you want to describe its time derivative in some kind of flow setting.
Yeah.
that time derivative is given by, and if you assume that the first cohomology is zero, then it's given by a global function.
Exactly, yeah. No, and then, like I said, this much in many different settings, I understand for the generalized Caylor Ricci flow, and that is very useful, and it does lead to, you know, some structure and whatever, but you know, to be able to describe that the time t data in terms of one scalar function and background data would be immensely useful. But maybe it's just not possible. But on the other hand, I mean, there is this local description in terms of one function. You can describe literally everything, right, in terms of this capital K. Again, assuming the sort of big omega is fixed, assuming you know
but
this
sorry,
other
so I'm trying to understand, like in the usual Caylor case, can you say, like, presumably you already have the Holy Grail in the Caylor case?
Yes, exactly.
And what is that Holy Grail?
It's
case?
just the usual Caylor potential. So the Caylor potential evolves,
which
again,
is not global.
Sorry, yeah. Well, you have a one parameter family of functions that's evolving by basically this Monge-Ampere type equation, which again fits into this same spinor norm point of view.
Yes.
But anyways, but then the point is the time t metric is the original metric plus IDD bar of u or f, whatever you want to call it. You get a global description in time, space and time, in terms of the initial metric and IDD bar of f. I mean, in this.
But that's local. I don't get it. Sorry.
No, that's a global formula. The global formula is omega t is omega 0 plus IDD bar ft.
Oh, because you're staying inside the scalar class.
Yeah, the class is fixed, right?
Maybe to clarify, in the Caylor case, we have this idea of Caylor class, which is the Durham class of the Caylor form. Okay,
yes.
So what's the analog here? So there are various points of view. So one candidate of analog is to fix the Poisson tensor Q, or the imaginary part Q, and the cohomology class of F. And from what we hear here, if B1 is 0, then indeed, I think infinitesimally, we'll have generalized scalar structure of that type, parameterized by functions, by the flow construction of the functions, which really resembles what Jeff.
But I guess the thing that I'm kind of wondering about is that because you're not because the differential equation can be put into this Hamiltonian formalism, where you know you're flowing this Lagrangian brain. It doesn't seem to me to be like a local thing in the sense of in the sense that you mean. I mean, it seems to me that you are. The problem is that you would get the same type of expression. It's just that it wouldn't be DD bar of a function. It would be this kind of flow construction version of it, this averaged version of it.
Well, yeah, I guess, and like I said, with this much we sort of can derive. I guess, like you say, we fit it into this flow construction, and useful as that is, what I'm asking for would be more useful.
But okay, so I'm dense, obviously, because I still don't see the difference. The difference is that you have omega naught plus DD bar of f versus omega naught plus integral DD bar f sub s.
Well, yeah.
But Marco, even that is not clear in general, because the flow will not preserve the Durham class of capital F in general. It only does on Calabi-Yau, on Hyperkaler.
So, but I mean, but even assuming that, sorry, go ahead.
So it's more like a function in a closed form that in general will be involved.
Oh, I think I understand what you're saying. I think Francis explained that there's two parts. Like one part of the flow might be that you're changing Z, the holomorphic data, right? But that you can separate out. So what that should be separated out, and then the question then becomes, like on a fixed Z, how does that thing move? And in that case, the cohomology class should be fixed of F. I mean, it's like it's like in the deformation of Calabi-Yau, right? I mean, you could imagine changing the complex structure as well.
Yeah.
Yeah, I don't know. I'm confused. Maybe the Holy Grail is there on the table and you just don't know because it's like surrounded by a bunch of glasses that all look the same.
Well, I don't want to be like the guy in Indiana Jones, you know, who drinks the wrong cup. But yeah, in any case,
maybe a sensitive question to ask is if you fix Z and omega and you let L evolve by a Hamiltonian isotopy, then if the function generating the Hamiltonian isotopy is such that satisfies generalized Ricci flow, once you write down everything in terms of the deformation data, then what is the PDE for that function?
Sorry, when you say that function,
I agree.
You mean like the FT sort of? Like the little f?
Yeah. Yeah, you could imagine taking a function on one of the sides, like on the x minus, suppose. You take a smooth function. Each time you give such a smooth function, you could pull it back to the Z space, and that will give you a Hamiltonian vector field that wants to flow that thing. So if you give a family of these functions, right, that will give you a time-dependent Hamiltonian vector field upstairs that will deform your GK structure. And so the question is, what is the different, if you write down generalized scalar Ricci flow for that family of functions, what is the
well, yeah, and if I'm understanding you correctly, I mean, I think at least in like this non-degenerate case, we have the answer. It's just that function evolves by phi, this capital phi, this sort of Calabi-Yau quantity.
Yeah.
And yeah, I mean that. Well, yeah.
In the general case, the Z space does evolve, though.
Right. Yes, definitely.
But I guess you know how it evolves because it evolves in a prescribed way. So,
yeah.
So then you just
it's moving in the direction of the canonical line bundle.
Yeah. So
the canonical line bundle is giving you like a class. That class is defining a Hitchin deformation of the Poisson structure and of the Z space.
But that deformation is independent of the function because the imaginary part of omega t is not evolving, is not changing.
Yeah, that's right.
And so when you look at when you look at the way that this L flows, it's going to flow by Hamiltonian vector field with respect to the imaginary part, which is fixed. So you have kind of two independent things. One of them is how is the real part of omega varying, and then how does L vary? And that's going to be with a time-dependent function flowing with the Hamiltonian flow of the imaginary part.
I mean, maybe it's worth kind of repeating this fact that when you it's just like in Kaler Ricci flow, right? They have the Kaler class, and then the Kaler class is sitting inside the Kaler cone, and then you have the canonical line bundle, and the canonical line bundle is pointing a certain direction in the Kaler cone, and it's making that Kaler class move. And sometimes it hits the boundary of the Kaler cone. And if that happens, then you're supposed to do some kind of blow up or blow down, right? But along the way, like that, during that time, the complex structure remains fixed.
Yeah.
And in this case, it doesn't.
Well, of them does.
Well, it doesn't really matter. I mean, you could put it on either side. There's or you could put both. You could make both of them flow. The point is that because the Kaler class is coupled to the Poisson tensor to give you a class in H1T, the class of the canonical line bundle is a class in H11. And that couples with the Poisson tensor to give a class in H1T. And that's telling you how the complex structure should move. So the topology of the situation is telling you to change the complex structure. So there's a prescribed road of complex structure deformation that you have to go along. And then you need to lift that path to the actual Kaler class, to the Kaler metric. So there is something fundamentally different which you don't see in Kaler-Ricci flow, which is that you're already on a trajectory of deforming the complex structure.
Isn't the class in H1T trivial? Is that?
Yeah, it will be trivial, I think, in the general.
That's true, but the Z space is a holomorphic symplectic manifold. So it has not just a holomorphic data, but sorry, it has not just its complex structure, but it also has the holomorphic symplectic form. So the holomorphic symplectic form is changing. I'm including that in the holomorphic data. Sorry, yeah. So there's a prescribed road of deforming the holomorphic substructure. That's what I mean. That you need to let that one go, and lift the Kaler metric.
Yeah.
It's kind of like it's kind of similar to what happens in a twister space, where you have the holomorphic symplectic structure is changing on the different fibers of the twister fibration, and you have this. Yeah, it's very similar to the idea that in the twister space fibration, that's a prescribed holomorphic family with a holomorphic symplectic form on it, on the fibers, and that's part of the twister data. And then there's an extra real data on top of that family that determines the metric. Those are the real twister lines, right? And so this is very similar. So when you decide that you want to do a GK flow, that's like defining you almost like a twister family in the holomorphic setting. And then you need to lift on top of that family, you need to populate it with a metric that depends on time. I don't know. This part is quite confusing, so I don't know if I hope that's right.
The analogy that I had in mind was like when you know that the cohomology class it kind of varies in the direction of the turn class. So what you do is you define it like if C1 corresponds, you pick a representative like that, and then you describe the deviation with a function. But if you think about what's going on with the twisted cotangent bundle, you have T star of M with omega naught plus the pullback of this thing. So kind of this thing that people usually do, you could just think of that as corresponding to deforming the affine bundle as a holomorphic symplectic manifold. And then when you want to actually describe the deformation, you have to add this kind of part, which is describing how LT would vary. Because this here in this picture, then it would be so I was trying to present this in a way that was kind of analogous to the usual picture. So this variation of the family, which is kind of fixed, is like, it's like this thing.
Yeah, indeed. Like if you think about a Kaler Ricci flow where you're changing the Kaler class.
Are you finished, Jeff?
Right. That Kaler class determines the twisted cotangent bundle as a complex symplectic manifold. And so as you're, when they draw that picture of the Kaler class moving in the Kaler cone, that's literally a path in the complex deformation space of the twisted cotangent bundle. The deformation theory of the twisted cotangent bundle. So it's purely holomorphic data that's changing. And then the Monge-Ampère equation is like happening with that underlying path being fixed. So maybe it would be useful to kind of imagine that you fix the path to begin with. Imagine that you fix the deformation of the Z, the holomorphic Poisson structures, the Z spaces, all that holomorphic data as a function of T, as a holomorphic function of T. Just fix the family to be, once and for all. And then on that thing, write the PDE for that function.
Yeah.
Okay, well, maybe that's a reasonable place to stop. Sorry, seems perhaps we should give people a chance to go to bed or whatever. But yeah, thanks for all those comments, Marco. It's a good. I mean, I think there's probably a lot more to come. So I'm going to be, in a sense, almost picking up where Francis left off. So yeah, I mean, I'll be going next. I think I'll start with some basic introduction to what's going on in Kaler-Ricci flow and what it is we're trying to generalize, and then sort of just try to focus on these kind of more fundamental geometric aspects of how all the generalized Kaler structure manifests itself in the flow, basically, so we can try to make some more progress there. But yeah, thanks again, Francis. It was a great sequence. Yeah. Thank you. I'm sorry, Marco, if I cut you off. But
no, I should shut up anyway. Okay. It's fine. Yeah. No. Thanks a lot, Francis. Bye. See you later.
Plenty more to come. So yeah, thanks everyone. Yeah, see you.